In this video, we're going to take a look at two problems that show up with PID controllers, the pure derivative and the pure integral. So let's start with the PD controller, or the derivative. So first of all, notice that the PD control law we can write as C of S is equal to Kp plus Kd times S. For simplicity, let's just let Kp equal 1 and Kd equal 1. And we can go ahead and calculate the magnitude of this control law, and we can plot that versus frequency. And what we would find is that if I have magnitude over here, and I have frequency here, as frequency increases, the controller starts with a magnitude around 0, and then at some frequency it starts to ramp up, and it goes off linearly in the log scale as frequency increases. So at higher frequency, we tend to get a lot of amplification of the signal, whereas at lower frequencies, we get roughly no amplification of the signal. This is in dB. And so what that means is that any signal with high frequency content gets amplified. Now, what does that have to do with anything? Well, if we think about a noise signal might be plotted like something over time, some fairly messy signal like that. Notice that at each one of these corners, that's actually a high frequency content, in the sense that I would need a lot of frequency in my Fourier expansion. I'll need a lot of values at high frequency to go ahead and cover those sharp curves. So in other words, what tends to happen is that derivatives amplify noise. And another way to think about this is, if I were to take the derivative of this signal, everywhere where I have a sharp peak, I'm going to get a very large derivative, because there's a very large change in the signal at that peak. What about the PI controller? The PI control law has the form that C of S is equal to Kp plus Ki over S. And again, let's let Kp equal 1 and Ki equal 1. If we go ahead and multiply through a common denominator, we find that Cs is equal to S plus 1 over S. And if we go ahead and take the magnitude of C of S and plot that, and again, I'm going to do this in dB, versus frequency, what we see is that we get a kind of an opposite response to the integrator, which is that it starts out at low frequencies. I have very high gain, and it comes down, and at some frequency it tends to come back towards 0. So the integrators amplify low frequency signals. And what this means is, if I have a step input to a system, then the first frequency that I could use to model that step would be a very low frequency signal, where I come in and do something like this. So that's a fairly low frequency sine wave. And this is known as integrator windup. And what it really is saying is that the integrator, right, collects information from the past as it's aggregating along, and it tends to have some memory, so it can't forget that. And as it collects this information and another large change comes along, it takes a while to respond to that. So the net result of this is that we tend to get a lot of overshoot from integrators. Obviously, integrators are great for reducing steady-state error, and derivatives are great for reducing overshoot, but they also have their the adverse effects. So what do we do about this? Well, the concept came along of what we call a lead or lag compensator. And again, it's just another control law that we say C of S is some gain K times S plus Z over S plus P. And this is sometimes known as a dynamic compensator, and it has that name because it's got derivatives and integrals in it, but it's also known as lead and lag. in this form, when Z is less than P, it's known as a lead compensator, and when Z is greater than P, it's known as a lag compensator. And these names come from looking at the magnitude and phase plots of this control law. So the reason that these are useful is because notice the following. When P gets small, or in fact in this case we can say let P equal 0, then our control law is given by K times S plus Z over S, which is just K times 1 plus Z over S. Well, this looks a lot like a PI controller. So when P is relatively small, so this would be a lead filter, then this approximates a PI controller. Likewise, as Z gets small, then it tends to look like a PD controller. And that's equivalent to having a lead filter versus a lag. We can look at the implications of taking derivatives and integrals and compare them with a lead filter by using Simulink. I have a switch here so we can select either a random signal or a step, and we can look at the signal itself, the derivative of the signal, the integral of the signal, and the lead filtered signal. We could change this to a lag filter if we like. If we go ahead and run this, and then we look at all these different signals. So first let's look at the noise itself. Notice that, it's just noise, has magnitude roughly around plus or minus 2. If we look at the derivative of the signal, we see that we have these very large magnitudes. Now this one obviously is a bit spurious, but if we go ahead and zoom in a little bit to something a little more manageable, now we can see that I have magnitudes roughly an order of magnitude 10 higher than the actual input itself. If we look at the integral of the signal, we notice that it's around 1 in terms of magnitude, and it tends to reduce the amount of noise. And if we look at the lead filtered signal, in this particular case, it actually doesn't change the magnitude of the noise very much. If we switch over to the step input, we can see the impact of the integrator in terms of integrator windup. Here's the integral of the signal, and here's the signal itself, the derivative of the signal, and the filtered signal. Notice the integral of the signal tends to start to grow without bound, which really what we're doing is integrating a constant, so we expect this kind of behavior, that this will grow linearly with time. Whereas the derivative has this spike, but otherwise then it's constant and 0, and whereas the lead filter tends to spike, but then it comes back and relax down to 0. So it doesn't suffer from the defect of integrator windup.